From the earliest days of human curiosity, people have tried to understand how everything began. When modern science introduced the idea of the Big Bang, it quickly entered popular culture as a dramatic image, a massive explosion, a cosmic firework blasting matter outward into a dark, empty void. This picture appeared in textbooks, documentaries, animations, and even casual conversations. Yet this mental image, powerful as it is, fundamentally misrepresents what scientists mean when they talk about the Big Bang. Neil deGrasse Tyson has repeatedly emphasized that the Big Bang was not an explosion in space. It was the expansion of space itself, a concept that challenges everyday intuition and forces us to rethink what words like beginning, movement, and even location truly mean on a cosmic scale. An explosion, as we understand it in daily life, always has certain features. It happens at a specific place. It throws material outward into surrounding space. There is a center, a boundary, and an environment into which the debris travels. A bomb explodes in a room. A star explodes into the surrounding vacuum. Fireworks explode in the sky. Our brains are trained by experience to interpret sudden expansions of energy and matter this way. When the term Big Bang was coined, it unintentionally triggered the same mental framework. People imagined a tiny universe exploding outward into nothingness. But the universe does not behave like a firework, and the Big Bang does not fit the definition of an explosion at all. To understand why, one must first let go of the idea that space is a passive stage where events happen. In modern cosmology, space is an active, dynamic entity. According to Einstein's theory of general relativity, space and time are woven together into a fabric that can stretch, curve, and evolve. The Big Bang marks a moment when this fabric was extremely hot, dense, and rapidly changing. As time progressed, space itself expanded, carrying galaxies along with it. The galaxies were not racing through space away from a central blast. Rather, the space between galaxies was increasing everywhere. A helpful way to imagine this, though imperfect, is to think of dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart. Each dot sees all the others moving away, yet no dot is the center of the expansion. Importantly, the surface of the balloon does not expand into something on its surface. The expansion is intrinsic to the surface itself. Similarly, the universe does not expand into pre-existing space. Space is what expands. This distinction is subtle, but it is the key to understanding why the Big Bang was not an explosion. When astronomers observe distant galaxies, they see that almost all of them are moving away from us, and the farther away they are, the faster they appear to recede. This relationship, known as Hubble's law, is often misinterpreted as evidence that we are near the center of the universe. But the same pattern would be observed from any galaxy. Every observer, no matter their location, would see distant galaxies moving away. This only makes sense if space itself is expanding uniformly, not if matter is flying outward from a central point. The misconception of explosion also leads to the false question: where did the Big Bang happen? If it were an explosion, it would make sense to search for its location. But in an expanding space model, the Big Bang happened everywhere. Every region of space we see today was once compressed into that early, dense state. The atoms in your body, the air you breathe, the ground beneath your feet, all of it traces back to that same initial condition. There is no privileged location where it all began. The universe does not have a cosmic scar marking the site of its birth. This idea often feels uncomfortable because human intuition evolved in a world of small distances and familiar forces. We instinctively imagine space as a container and matter as something moving inside it. Cosmology asks us to reverse that thinking. Matter and energy exist within spacetime, and spacetime itself can change. When the universe expands, it is not that galaxies are pushing against space. Space is stretching between them. This is why galaxies are not torn apart by expansion. On smaller scales, forces like gravity and electromagnetism dominate, holding atoms, planets, and galaxies together. Expansion becomes noticeable only across vast, intergalactic distances. Neil deGrasse Tyson often points out that bad metaphors can be more dangerous than no metaphors at all. The explosion metaphor may make the Big Bang feel accessible, but it plants misconceptions that are hard to uproot. For example, people ask what caused the explosion, what set it off, or what existed outside the universe at the time. These questions assume the universe behaved like an object sitting in space, waiting to explode. In reality, the Big Bang describes the evolution of space, time itself, not an event occurring within a larger environment. The early universe was not empty space waiting to be filled with matter after an explosion. It was already full of energy, particles, radiation, and intense heat. As space expanded, that energy spread out and cooled. This cooling allowed fundamental particles to form, then atoms, then stars and galaxies. The expansion did not fling matter into existence. It changed the conditions that allowed structure to emerge. In this sense, the Big Bang is better thought of as a transformation rather than a detonation. Another source of confusion comes from the way time is treated. In an explosion, time exists before the event, during the event, and after the event. With the Big Bang, time itself is part of what is being described. When cosmologists trace the universe back to its earliest moments, they are not just rewinding matter's motion through space. They are approaching a boundary where our understanding of time itself becomes unclear. Asking what happened before the Big Bang may be like asking what happened before time began a question that might not have a meaningful answer within our current theories. The expansion of space perspective also reshapes how we understand cosmic history. The Big Bang was not a single instant of chaos followed by calm. It was the beginning of an ongoing process. The universe has been expanding for billions of years and continues to expand today. In fact, observations suggest that this expansion is accelerating, driven by something we call dark energy. This means the Big Bang is not merely an ancient event locked in the past. Its effects are still unfolding. We live inside the aftermath of that expansion, not as passive observers, but as participants embedded within space-time. Understanding the Big Bang as expansion rather than explosion also highlights the humility of science. The theory does not claim to explain everything. It describes how the universe evolved from an early, hot, dense state to what we see today. It does not pretend to know why that state existed or whether something preceded it. By correcting the explosion myth, scientists are not taking away wonder. They are replacing a simplistic story with a deeper, more accurate mystery. Neil deGrasse Tyson emphasizes that science communication must balance clarity with truth. When accuracy is sacrificed for drama, misunderstandings multiply. The phrase Big Bang itself is somewhat unfortunate, yet it remains because of historical momentum. What matters is not the name, but how we interpret it. Once we accept that space itself expanded, many puzzles fall into place. The absence of a center makes sense. The uniformity of the cosmic microwave background becomes understandable. The large-scale structure of the universe emerges naturally from tiny fluctuations stretched by expansion. In the end, letting go of the explosion image does more than correct a technical error. It changes how we see existence. We are not standing in the debris field of a long, forgotten blast. We are embedded in a universe whose very fabric has been unfolding for nearly 14 billion years. Space is not static, empty, or indifferent. It has a history, it has dynamics, and it carries within it the story of everything we see. When people say everything they know about the Big Bang is wrong, the statement is not an attack on science, but an invitation to think more deeply. The universe is not obliged to match our intuition. The Big Bang, understood properly, is not less impressive than an explosion. It is far more profound. The idea that space itself can stretch, evolve, and shape reality challenges the limits of imagination. And in embracing that challenge, we move closer to understanding the true nature of the cosmos, not as a shattered remnant of an ancient blast, but as a living, expanding tapestry of space and time. When people hear that the universe began with the Big Bang, they often imagine everything compressed into a tiny dot, a single point floating in darkness, which then burst outward to form stars, galaxies, and space itself. This idea feels natural because it matches how explosions behave in everyday life. Something small expands into something larger, and there is always a place where it started. Yet this mental picture, while common, is deeply misleading. One of the most important corrections emphasized by Neil deGrasse Tyson is that the universe did not begin as a tiny fireball at one location. There was no single spot in space where the Big Bang occurred, because space itself was part of what came into being. To understand this, it helps to reconsider what is meant by size and location in the context of the early universe. When cosmologists say the universe was once very small, they do not mean it was a compact object sitting somewhere. They mean that the distances between all points in space were much smaller than they are now. The universe may have already been infinite in extent, even at the earliest moments we can describe, or it may have been finite but unbounded. In either case, it was not a tiny ball surrounded by emptiness. Every region of space was filled with energy and matter, and every region was expanding away from every other region as time progressed. This idea clashes with everyday intuition because human experience is rooted in local, finite environments. We think of objects as having boundaries and positions. We imagine beginnings as points and origins as locations. But the universe does not conform to these expectations. The Big Bang was not an event that happened at a particular address in cosmic space. It was a state in which the universe was hot, dense, and rapidly evolving. As time moved forward, that condition changed uniformly everywhere. A powerful way to see why the single location idea fails is to consider astronomical observations. When we look at distant galaxies, we see that they are moving away from us, and the farther away they are, the faster they appear to recede. At first glance, this seems to suggest that we are at the center of the universe, but astronomers quickly realized that this interpretation does not hold. If observers in a distant galaxy made the same measurements, they would see the same pattern: galaxies moving away in all directions. This symmetry tells us that the expansion is not centered on any one point. It is a property of space itself. If the Big Bang had occurred at one location, we would expect to see a preferred direction in the universe, a gradient pointing back toward the center of the explosion. But instead, on large scales, the universe looks remarkably uniform in every direction. The cosmic microwave background radiation, a faint glow left over from the early universe, has nearly the same temperature across the sky. This uniformity would be difficult to explain if everything had flown outward from a single spot. It makes much more sense if the early universe was uniformly hot and dense everywhere. The misconception of a single starting point also leads to another common question: where are we located relative to the beginning? People ask whether Earth is near or far from the center of the universe. The answer is that such a question has no meaning. There is no center. Every place in the universe is as central as any other, because the expansion occurs uniformly throughout space. This idea can be unsettling, as it removes the comfort of a fixed reference point, but it is one of the most profound insights of modern cosmology. Neil deGrasse Tyson often highlights how visualizations can unintentionally reinforce the wrong idea. Animations frequently show a small glowing sphere expanding into a larger one, surrounded by darkness. While visually appealing, these images suggest that the universe had an edge and a surrounding environment. In reality, the universe does not have an edge in the way objects do. If it is finite in a way that does not require a boundary, much like the surface of a sphere has a finite area but no edge. If it is infinite, it was infinite even at early times. In both cases, there is no outside, into which the universe expanded. The early universe was not empty space waiting to be filled. It was already full, but in a different form. Matter as we know it today, atoms, molecules, solid objects, could not exist under the extreme temperatures of the early cosmos. Instead, energy, elementary particles, and radiation dominated. As the universe expanded and cooled, conditions gradually allowed protons and neutrons to form, then atomic nuclei, then atoms themselves. Later still, gravity pulled matter together to form stars and galaxies. This process did not begin at a single location and spread outward. It happened everywhere at once, governed by the same physical laws. Understanding that the universe did not begin at one point also changes how we think about the phrase, the size of the universe at the beginning. Popular descriptions often say the universe was once the size of a grapefruit or smaller than an atom. These comparisons are meant to convey density, not literal spatial extent. They compress the entire universe into a familiar object to make the idea feel manageable. But taken literally, they reinforce the false notion of a tiny universe located somewhere. In reality, the early universe was dense because everything was close together, not because it was confined to a small region of space. This distinction becomes even more important when considering questions about what lies beyond the observable universe. We can only see a finite portion of the cosmos because light has traveled for a finite amount of time. Beyond that observable horizon, space may continue much farther, possibly infinitely. Those distant regions were also part of the same early universe and followed the same expansion. The Big Bang was not confined to what we can observe. It applied to all of space, whether we can see it or not. Neil deGrasse Tyson's emphasis on this point is not just about correcting a technical misunderstanding. It is about reshaping how people think about cosmic origins. When we imagine the universe starting at a single point, we impose humans, thinking on a reality that operates by very different rules. Letting go of that image opens the door to a more accurate and more awe-inspiring view. The universe was not born in one place, it was born as a whole. This perspective also affects philosophical questions. If there was no single location where everything began, then the search for a cosmic birthplace becomes meaningless. The universe does not have a spatial origin in the way cities or mountains do. Its origin, insofar as we can describe it, is a change in the state of space, time itself. That realization shifts the focus from where did it happen to how did conditions evolve. The absence of a central starting point also reinforces the idea that the laws of physics are universal. The same processes that governed the early universe here governed it everywhere else. There was no privileged region with different rules. This uniformity is one of the reasons cosmology can be studied scientifically at all. By observing the universe from our small vantage point, we can infer its history on the largest scales. In the end, understanding that the universe did not begin as a tiny fireball at one location strips away a comforting but incorrect story. What replaces it is something both subtler and grander. The early universe was not a point in space. It was a condition of space. Every part of the cosmos shares that origin. Every galaxy, every star, every atom traces its history back to a time when the universe was uniformly hot and dense everywhere. This idea can be difficult to visualize, but its implications are profound. It means that the Big Bang was not an event that happened somewhere far away and long ago. It happened here, where you are now, and everywhere else too. The space you occupy today was once part of that early, intense state. By understanding this, we move closer to what cosmology is truly telling us. Not a story of a cosmic explosion at a distant point, but a story of a universe that began as a whole and has been evolving everywhere ever since. One of the most persistent ideas about the Big Bang is that it represents a clear, absolute beginning of everything, the moment when the universe suddenly appeared out of nothing. This belief is reinforced by dramatic language, simplified explanations, and even philosophical or theological interpretations that go far beyond what the science itself actually claims. Neil deGrasse Tyson frequently stresses that what we call the beginning of the universe is not necessarily a true beginning of existence, but rather the edge of our current understanding. The Big Bang marks the limit of the physics we can reliably describe, not a definitive statement about what reality was or was not before that moment. When cosmologists talk about the Big Bang, they are referring to a period in the early history of the universe when it was extremely hot and dense. The theory describes how the universe expanded and cooled from that state, leading to the formation of particles, atoms, stars, and galaxies. What the theory does not do is explain why that state existed in the first place or whether something preceded it. This distinction is crucial. The Big Bang is a model of evolution, not a complete origin story. As scientists mathematically trace the universe backward in time using general relativity, they encounter a point where the equations predict infinite density and temperature. This point is often called a singularity. In popular explanations, the singularity is treated as a real physical object or event, the instant when everything began. But in physics, a singularity usually signals a breakdown in the theory being used. It is not necessarily a description of reality, but an indication that the model has reached its limits. To understand this, it helps to think about historical examples in science. Before quantum mechanics, classical physics predicted that atoms should be unstable, with electrons spiraling into the nucleus. The prediction was not a discovery of real behavior, but a sign that classical physics was incomplete at very small scales. In the same way, the singularity at the start of the Big Bang does not mean the universe truly reached infinite density. It means that general relativity alone is not sufficient to describe those earliest conditions. Neil deGrasse Tyson often emphasizes that science is honest about what it does not know. Saying, "We don't know what happened before the Big Bang," is not a weakness, it is a strength. It reflects a commitment to evidence and testable models rather than speculation. Many people feel uncomfortable with this uncertainty and prefer a simple answer that provides closure. But the universe does not owe us closure. It offers clues, not final answers. The idea that time itself may have begun with the Big Bang further complicates the notion of a before. Time, in modern physics, is not an independent backdrop against which events unfold. It is intertwined with space. If space, time itself, emerged from the Big Bang, then asking what happened before it may be like asking what is north of the North Pole. The question assumes a framework that does not exist. This does not mean there was nothing before the Big Bang, but it does mean that our current concepts of before may not apply. Some theories attempt to extend our understanding beyond this boundary. Ideas such as cosmic inflation, bouncing universes, cyclic models, and quantum gravity propose ways the universe might have existed in some form prior to the hot, dense state we call the Big Bang. These ideas are fascinating and actively researched, but they are not yet confirmed by direct evidence. Neil deGrasse Tyson is careful to distinguish between well-supported science and speculative but promising hypotheses. The danger arises when speculation is presented as fact. Popular culture often treats the Big Bang as the moment creation itself happened. This framing can blur the line between scientific explanation and metaphysical interpretation. Science, however, deals with how the universe behaves, not with ultimate purpose or meaning. The Big Bang theory explains how the universe evolved from an early state, not why there is something rather than nothing. Confusing these questions leads to misunderstandings about what science can and cannot answer. Recognizing the Big Bang as a boundary of knowledge also helps clarify debates about certainty in science. Some people interpret the absence of answers about the absolute beginning as a failure of cosmology. In reality, it reflects the depth of the question being asked. Understanding the origin of space and time is one of the most profound challenges imaginable. That modern physics can trace the universe back billions of years with remarkable accuracy is an extraordinary achievement, even if it cannot yet describe the very first moment. Neil deGrasse Tyson often reminds audiences that scientific theories are not static truths carved in stone. They are models that improve as new data and better mathematics become available. The Big Bang theory itself has evolved over time. Early versions were simpler and less detailed. As observations improved, the theory incorporated cosmic background radiation, nucleosynthesis, and large-scale structure. Future discoveries may further refine or even radically reshape our understanding of the universe's earliest moments. This perspective also protects science from overreach. When scientists acknowledge the limits of their theories, they avoid making claims that cannot be tested. The Big Bang theory remains powerful precisely because it does not pretend to answer everything. It focuses on what can be observed, measured, and modeled. Beyond that, it remains open-ended. The public desire for a clear beginning is understandable. Human stories often have a starting point, a middle, and an end. We like narratives with origins, but the universe may not conform to this storytelling structure. Its history may extend further back than we can currently imagine, or it may involve processes that do not fit neatly into human concepts of time and causation. Accepting this possibility requires intellectual humility. When people say everything you know about the Big Bang is wrong, they are often reacting to the realization that popular explanations oversimplify a deeply complex subject. The Big Bang is not a moment when something came from nothing in a way we can fully comprehend. It is the earliest chapter we can currently read in the cosmic story. The pages before it may exist, but they are written in a language we have not yet learned to interpret. Understanding this does not diminish the wonder of cosmology. On the contrary, it enhances it. The fact that there are limits to our knowledge invites curiosity rather than complacency. It encourages new theories, new experiments, and new ways of thinking. Neil deGrasse Tyson's role in this conversation is not to tear down the Big Bang, but to clarify what it truly represents: a powerful, evidence-based model of the universe's early evolution and a reminder that the deepest mysteries remain open. In recognizing the Big Bang as a boundary rather than an absolute beginning, we align our understanding with the spirit of science itself. Science advances by pushing against the edges of what is known, not by pretending those edges do not exist. The early universe stands as one of those edges. Beyond it lies a realm of unanswered questions, not because the universe is unknowable, but because our tools are still incomplete. And it is precisely that incompleteness that drives the ongoing quest to understand where we came from and what reality truly is. From the moment the Big Bang enters public conversation, images flood the mind: swirling fireballs, shockwaves racing through darkness, matter bursting outward from a single origin. These images are vivid, cinematic, and deeply memorable. Unfortunately, they are also deeply misleading. Neil deGrasse Tyson has often pointed out that many of the most familiar visuals and explanations used to describe the Big Bang are not just simplified, but fundamentally wrong in ways that distort how people understand the universe. The problem is not a lack of information, but the persistence of metaphors that feel intuitive while quietly reshaping the truth into something it is not. One of the most common visual mistakes is showing the universe as a small glowing sphere, expanding into a larger sphere surrounded by black emptiness. This depiction suggests that the universe has an edge, and that it is growing outward into an external space. In reality, there is no evidence that the universe has an edge, and there is no external space into which it expands. Space itself is the thing that expands. When visuals imply otherwise, they encourage viewers to think of the universe as an object inside a larger container, rather than as the totality of space-time. Another misleading explanation is the idea that the Big Bang was a moment of chaos followed by order. Many documentaries describe it as a violent, disorderly explosion that somehow settled down into the structured universe we see today. While the early universe was indeed hot and energetic, it was also remarkably smooth and uniform. In many ways, it was more orderly than the present universe. Tiny fluctuations in density existed, but they were extremely small. Over billions of years, gravity amplified those tiny differences, leading to the formation of galaxies, stars, and planets. The dramatic cosmic chaos narrative reverses this reality and hides one of the most fascinating truths. Complexity emerged slowly from near uniformity. Language itself plays a major role in shaping misunderstanding. Words like bang, explosion, and creation carry everyday meanings that do not apply at cosmic scales. When educators or media rely on these words without careful explanation, they unintentionally reinforce false assumptions. Neil deGrasse Tyson often emphasizes that science communication must be precise, even when aiming to inspire. Inspiration built on incorrect ideas eventually collapses under scrutiny. Another popular misconception is that the Big Bang can be visually imagined at all. People ask what it looked like, what color it was, or what it sounded like. These questions assume that the early universe could be observed like an event in space, with light, sound, and perspective. But sound requires a medium, and light as we know it could not travel freely in the earliest moments of the universe. The universe was opaque, filled with charged particles that scattered radiation. Asking what the Big Bang looked or sounded like imposes human sensory expectations on a reality that existed under conditions far beyond everyday experience. Even timelines can mislead. Charts often show a neat sequence of events beginning at 0 time and unfolding in an orderly fashion. While these timelines are useful, they can give the impression that scientists know exactly what happened at the very first instant. In truth, our knowledge becomes increasingly uncertain the closer we get to the earliest moments. Presenting a smooth, confident narrative all the way back to time 0 can hide the genuine limits of scientific understanding. Neil deGrasse Tyson stresses that these misleading explanations are not harmless. They shape how people think about science itself. When simplified stories are later corrected, some feel betrayed, as if science keeps changing its mind. In reality, science improves its explanations as understanding deepens. The problem arises when early explanations were never accurate to begin with, but were tolerated because they seemed easier to communicate. The danger of misleading visuals becomes especially clear when people ask questions like what happened before the Big Bang, or what is outside the universe. These questions are natural, but they often stem from incorrect mental models. If one imagines the universe as an object expanding into space, then it makes sense to ask what lies beyond it. If one understands the universe as all of space-time, the question changes entirely. It becomes not about location, but about physical laws and their domains of applicability. Neil deGrasse Tyson frequently advocates replacing misleading images with better, though still imperfect, metaphors. Stretching space, expanding grids, and raisin-bread analogies are attempts to shift thinking away from explosions and toward expansion. While no analogy is perfect, some at least point in the right conceptual direction. The goal is not to make the universe seem simpler than it is, but to avoid making it wrong. Another issue is the tendency to personalize or dramatize the universe's origin. Narratives often describe the universe as born or created in a way that mirrors human life events. While poetic, this framing introduces emotional and philosophical assumptions that science does not require. The universe does not need to be born in the human sense to be studied scientifically. Neil deGrasse Tyson emphasizes that poetic language should not replace precise explanation. Correcting these misconceptions does not make cosmology less engaging. On the contrary, the real story is more astonishing than the simplified one. A universe that expands everywhere at once, that begins in an almost perfectly uniform state, and that evolves complexity over billions of years through simple physical laws, is far more profound than a cosmic explosion in empty space. The challenge is trusting audiences to appreciate this deeper story. Understanding how visuals and explanations mislead also reveals something important about human cognition. We rely heavily on imagery to understand abstract ideas. When the imagery is wrong, understanding suffers. This is why careful communication matters so much in science. Neil deGrasse Tyson's criticism is not aimed at curiosity, but at complacency. The acceptance of comforting pictures without questioning whether they reflect reality. When people finally let go of the familiar Big Bang images, a different perspective emerges. the universe becomes less like a fireworks display and more like an evolving fabric. Space stretches, energy cools, structure forms. There is no edge, no outside, no central blast site. The universe does not behave like an object in space because it is space. In this light, the phrase, "everything you know about the Big Bang is wrong," is not an insult, but an invitation. It invites people to unlearn the shortcuts and embrace a more accurate, if more challenging, understanding. It reminds us that the universe is under no obligation to match our expectations or our favorite pictures. By confronting the misleading visuals and explanations head-on, we gain not only a clearer view of cosmology, but also a deeper respect for the process of science itself. Science advances by refining ideas, discarding bad metaphors, and replacing them with better ones. The Big Bang, understood properly, is not a failure of imagination, but a triumph of careful thinking. And in learning to see past the images that mislead us, we come closer to seeing the universe as it truly is.